So today we basically extend what we talked on yesterday. Yesterday we talked about inductive reasoning, or finding a conjecture just based on patterns or evidence. Very useful, and generally most kind of conclusions and rules we find start from inductive reasoning. Generally we see a pattern, we see something happening, it gets extended, and then we try to make it a little more logically sound. So inductive reasoning is often how it starts, but we can't guarantee that something is true just based on inductive reasoning, right? That's saying in most cases, or in these cases we've checked. You could, I suppose, prove something is true with inductive reasoning if you can check all examples. So like that one we looked at, the 1, 2, 3, 4, 5, 6, 7, 9 times 1 times 1 times 1 times 2. We could prove a certain set that this is just in all cases. We could say, for every number from 1 to 9, this pattern we found is true. And we can do that because we've shown all possible examples for all whole numbers. But inductive reasoning, in order to prove something with it, you have to be able to show every case is true. So for most theorems, it's not possible to show all cases. In fact, one of the most famous theorems in graph theory that don't make weird stuff, but it's called the four-color theorem. And it's never actually been proven. It's not a theorem. And that's because there's no way yet to generalize. So people have tried to try every kind of drawing and stuff to disprove it. But as of now, it's disproven. It's kind of proven-ish by induction. Proven-ish by showing enough examples where it works. But not been logically proven yet. Inductive reasoning cannot be used to prove a conjecture, but logic can. So let's start with a nice little logic, very straightforward logical reasoning exercise. So as soon as you dropped off film at quick 1 hour photo, they advertise that your film will be developed within 1 hour or there's no charge. She dropped her film off at 10 a.m. It wasn't developed until 11:15 a.m. Using deduction, what can she use? She gets free film. It's kind of a dated example. I don't think too many people are dropping film off anymore. But yeah, she should get it for free, right? Yeah. What's the domino rule? Pizza delivered within a certain amount of time? 35 minutes, 30 minutes? In general, lots of pizza places will have pizza by X amount of time, or else get it free. And you're always hoping, come on, be just a little too slow, be just a little too slow. Okay. So deductive reasoning is where we use true statements to arrive at a conclusion. She recognized if they say film developed in an hour or else it's free, her film was not developed in an hour, so therefore it's free. Okay? Let's figure out a conclusion that can be deduced from each of these. Every whole number is an integer. Right? Whole numbers are the integers greater than 0. 6 is a whole number, so we can deduce that 6 is also an integer. Or if we're using 30-2 language, whole numbers are a subset of integers. 6 is a whole number, so then, yeah, 6 is also an integer. How about this? Water freezes below 0 degrees. The temperature is negative 15. What can you tell me about water? Yeah, if water freezes below 0, the temperature is negative 15. Water's frozen. Although, there would actually be another piece here that some of you have probably run into. Those of you that like going for swims in the river in the middle of winter. On a day where it's colder than minus 15, Mars like, yeah, that's what I do every day. So, sometimes the water won't be frozen at negative 15, right? There maybe is actually another piece here that, water that is still and below 0 degrees is frozen. But it's possible in the river, right, that moving water that isn't actually as cold as the air. So we could add more details. But if both statements are true, water freezes below 0 and the temperature is negative 15, then we know in this case water is frozen. Now, we can talk about validity and truth. In this case, water may not freeze in every case below 0. If water is below 0, it freezes, but sometimes the water won't actually get below 0 there. If that statement is true, though, then we know that it follows if the temperature is -15, then the water's free. So validity, the argument is valid, the statement could be true or false. Yep.
Because this unit is so short, are we gonna have like a little quiz on the side, or are we just gonna get right to the exam?
Oh, good question. I'm planning to give you a quiz on Friday because I will be in the gym on Friday. So we're gonna do today's lessons, lesson 2. The quiz will be up to today. Tomorrow you'll have another lesson though, and then on Friday we'll have a quiz on the first 2 lessons. Monday we'll finish the unit. Tuesday practice test. Wednesday test. Okay. Lesson 4 in your book is not exactly how we're going to do this. It'll be a little bit different. I'm going to give you some different logic games. So it'll end up broken in pieces. But
So from yesterday to today's nation.
yeah, that's right. That's right. Yep. Okay. So a theorem is more than just conjecture. A theorem is a statement that can be proved using logical or deductive reasoning. So notice I said there's that famous graph theory problem called the 4-color theorem. It's called a theorem, although actually, technically, it has not been proved. It's more like the 4-color, very rigorous conjecture. Right? A theorem can be proved by logical reasoning, whereas a conjecture is just suggested by inductive reasoning. Okay. So last class, we used deductive reasoning to write the conjecture that 3 consecutive integers are divisible at 3. I'm going to show you how I use deductive reasoning to prove that. So we did it with some examples. We did, for example, the example that like 2 plus 3 plus 4 equals 9. And we recognized that was like 3 times 3. It's 9, right? We did that with a few of them. Yeah. But when I'm using numbers like this, I'm not in deductive reasoning. I'm in inductive reasoning. We're showing examples. Deductive reasoning is taking the general case, doing the thing with some variables we're talking about. So first of all, I want to write out 3 consecutive integers. Let's call the middle one n. Okay, n for number. So we have n. What's 1 less than n? How can I write out 1 less than n? Yeah, sure, n minus 1. N minus 1, or negative 1 plus n, sure. So n minus 1 plus n, and then what's more than n? Okay, hold on. Yeah, sure, n plus 1. Yes. And we're saying is a multiple of 3. It's a multiple of 3. So we're saying it must be 3 times 3 times 3. Now, is there a way we can prove that? That's what I'm suggesting. Let's just check and see if that's true. I guess even before I get there, let's see if that happens when I do this. If I just simplify this side, this expression, let's see what we get. Well, n minus 1 plus n minus 1. If I just now get rid of the brackets, there's nothing multiplying outside. So n minus 1 plus n plus n plus 1. Let's collect like terms. I see minus 1. Oh, sorry. I see minus 1 plus 1. What's negative 1 plus 1? 0. Okay. So then I have n plus n plus n. 3n. I think we've just proven that 3n must be a multiple of 3, assuming that n was an integer, right? And we said initially that n was an integer. So the sum of any 3 consecutive integers is a multiple of 3. Yes. 3n is divisible by 3. And something like this, there's kind of a communication piece here that's fairly important. By doing this stuff on the left here, we've shown that this is true. We've given a proof. We call this given a proof of what we're trying to say. So it would be worth at this point saying something like, therefore, and those 3 dots like that is therefore. Therefore, this conclusion is true. Or something like that, right? We're saying what was said above fits. It's true. It's right. By this deduction, by this logical reasoning, we see that what we said is true. Okay, just in general, I've found for most students, this is the first time you ever run into proofs in math. So in general, this lesson, there's a little bit of like, oh, I don't know how to do this. At this point, just try to think, okay, can I follow along with what he's doing? You are going to have to generate proofs. But at this point, first of all, it's okay. Can I just see with you? I see with you. So I'm trying to take The general case, sorry, I erased that one in a second. Trying to get a general case of n minus 1 plus n plus 1. 3 consecutive integers, and I'm trying to prove that it's divisible by 3. Yes, 3 is. Okay, how about this? I think you guys will like this. So pick a number less than some number you like. Okay, yeah, why don't we do one together first? We'll do one first. So I'm picking 9. By the way, I already hear someone saying a number that isn't necessarily just 1 to 10, right? It could be any number than less than 10, theoretically. So maybe it could be negative, maybe it could be a decimal, sure, whatever. But I'm going to try with 9. 9, okay. Add 7. Multiply by 2. Subtract the original number. Subtract 2. Subtract the original number. Okay. So I did that with 9. Now I better try another test case. First, choose a number less than 10. Yeah.
3.
Okay, add 7. Multiply by 2. Subtract the original number. Subtract 2. Subtract the original number. Okay, I'm starting to get an idea of what might happen here. Try another number. 6. Should we be more interesting? Can it be something that's not an integer? Or sure, yeah. Let's say not a whole number. Negative 2 is a great one. Good idea. Negative 2. Negative 2 plus 7, 5. Multiply by 2, 10. Subtract the original number. Oh, the original number was negative 2, so 12. Subtract 2, 10. Subtract the original number, 12. Oh, or negative.
Wow.
Okay, so far, I've done some inductive reasoning. I've tried some examples. And I've seen so far, my conjecture would be these operations, yeah, sure, lead us to a final value of 12, or something like that, right? Something like that. You may have said it more elegantly than me. When you choose a number less than 10, then add 7, then multiply by 2, then subtract the original number, then subtract 2, then subtract the original number, you get a value of 12. Now let's see here. I want to prove this with deductive reasoning. By the way, this is an example. Not exactly this, but you're going to have to do almost this idea on the example. So let's do the general case. I'm going to call my general case n. That's number less than 10. Do you like it? It's a nice number. Now I want to add 7 to my number, so I have n plus 7. Now I want to multiply by 2. 2 times n plus 7. Now I want to subtract my original number. Okay, 2. Oh, by the way, sorry. I should probably simplify this. 2 times n plus 7 is 2n plus 14. Right? If I distribute my 2 through the brackets. So I've now been asked to subtract my original number. Okay, so I have 2n plus 14 minus n. Or if I combine like terms, I have n plus 14, right? 2n minus n is n. And now I've been asked to subtract 2. So I have n plus 14 minus 2. Or if I combine like terms, I have n plus 12. And now I've been asked to subtract the original number, n plus 12 plus minus n. N minus n. Kind of interesting. By the way, does anyone think we have an example? Can you give me a counterexample here?
What about like no?
We've proven with deductive reasoning that this should work, so I'm pretty confident. But I still always feel like, okay, I did this with some magical math, maybe I did something weird, so I'm going to try a few more crazy examples to check. Yeah, sound good, Dawson? So why don't I try something else crazy just to check? I heard negative 100, I'd be very curious about that, sure. Let's try one more here. Negative 100 is my number, add 7, negative 93. Multiply by 2, is that negative 186. Subtract the original number. Subtract the original number. Okay, minus negative 100, so I'm at negative 86. Subtract 2. I'm at negative 88. Subtract the original number. Minus negative 100. Right. Negative 88 minus negative 100. I'll just roll this. I also, one of my favorite questions, someone did this was, said, oh, let's just try this with pi. Let's see what happens with pi.
Yeah.
It's a number. It's not a rational number, but we can try that. 3.1415926535, blah, blah, blah. So let's add 7. Okay, I have pi plus 7.
Okay.
Which is like 10 point whatever. Okay, multiplied by 2, so I have 2 pi plus 14. Subtract the original number, now I have pi plus
2.
Subtract 2, pi plus 12, minus pi, right? So in this case, we've shown using deduction that it was robust, and then we're like, I don't believe it, I don't believe my proof, I tried 2 more crazy numbers. Oh yeah, it does work. You can trust it. Or in this case, all numbers live at 12.
The only reason it works, right? It's the get rid of those.
Hey, by the way, did anyone try with a number bigger than 12?
Let me try.
Or bigger than 10? We didn't try that.
It doesn't even matter.
You're right. It's not.
This guy gave away.
Oh, you try? Let's try 11. 11 plus 7 is 18. Multiplied by 2, 36. Subtract the original number, 25. Subtract 2, 23. Subtract the original number, 12. Alright. Now a couple notation things for using deductive reasoning. Even numbers, call them 2n. Odd numbers, call them 2n minus 1 or 2n plus n, or plus 1. I've seen sometimes students going, oh, I'll just call 2n all even numbers, and I'll just call n all odd numbers, forgetting that n is a set that could include even and odd numbers. So we want to say every odd number is one off of an even number. So if we're calling 2n all even numbers, then odd numbers should be one more or one less than the even number. Or maybe more even robust, if you look at my number line, we call odd numbers red and even numbers blue. I'll give you an example. Right? 2n or 2n minus 1. So why can 2n be used to denote every even number? Any idea? Why would we do that? Why would 2n be able to be used for every even number?
Because
Right, by definition, every even number is equal to what 2? Or it's a multiple 2 of 2.
same difference.
And then why can 2n minus 1 be used to denote every odd number, while the numbers between evens are odds, right? One number off of an even number is odd. It'll be helpful once you're using this. Okay, so when 2 odd numbers are added, their sums are always equal. Okay, so first let's use inductive reasoning. Let's try 3 cases to see this. Okay, 2 odd numbers. I need Ileana, give me one odd number.
7.
7. Okay. Kathy, give me one.
9.
7 plus 9 is 16. Okay, nice. Alright, Milkias, give me an odd number. 19. Nibble, give me an odd number. 37. 36. Nice. And let's go Dimitri, odd number. 11. 43. We gotta get a little more interesting. 154. Will this work if it's negative 2?
Yeah.
Negative 7 plus, let's say plus positive 9 or something like that. Oh yeah, that's a positive 2. Okay, so by induction, I'm like, oh, I'm concluding this is probably true. My conjecture is likely true. Okay, what about proof though? Let's make a proof. Actually, why don't I give you a moment here? Why don't you try this? See if you can do this. This is kind of hard. See if you can take 2n minus 1 and 2m minus 1, and see what happens if you add 2 odd numbers. See if you can prove that it will be even. Try that.
The two odd numbers to the thing.
Yeah, but do it with the general case here. See if you can do some deduction.
Wait, do what add numbers to have right?
So you're going to set it up something like this. 2n minus 1 plus 2n, or 2m minus 1. And just see what happens when you combine like terms. Yeah, there's actually not too much to do here. The only like terms are the numbers. So you end up with 2n plus 2m minus 2. And if I was looking for what's a common factor from all of these are all divisible by 2. So I could say, okay, this is 2 times n plus m minus 1. And, well, what I know from above is this is a number. This is a number. It's some kind of integer. It could be positive, it could be negative, it could be even or odd. But now I know that it's some number times 2. Some number times 2. Or I could even say this is like, I don't know, 2 times p, 2 times whatever, some number. I've just proven that this is divisible by 2. This is an even number. So we could say something like, therefore, the solution is now something that's kind of hard initially when doing deductive reasoning is just knowing, have I actually proven anything? Did what I say actually prove what I mean it to say? And that's kind of a hard skill to build. But this is what we're going to try today. I would suggest that today's assignment is quite difficult. I'm going to give you this unit's exam. There's going to be one case where I sort of ask you to do a proof, but it's with that graph like I showed you. And there's going to be another case or two where I ask you to basically look at a proof and say what's good or bad about it, kind of where is the fallacy in the proof, and we'll talk about that more tomorrow. But for today's lesson, you're going to be trying to kind of step-by-step see how you can do a deductive proof. So for today, I want you to do, from section 2.2, I want you just to do questions 1 to 3. I'd like you to do all parts of them, but try just questions 1 to 3. Okay? Good. You have the rest of the lesson over. Yeah, the rest of the lesson, work on that while I eat this delicious Stifky toffee pudding.